Hello everyone, today we are going to discuss eigenspaces. Before we proceed, I assume that the viewers already know about eigenvectors and eigenvalues. If you're not sure what these topics are, feel free to refer to my videos about eigenvectors and eigenvalues. So I hope you coming here and then watching this session once you've understood what eigenvectors and eigenvalues are. And if you've understood what those terms are, AV equals lambda V should be clear by now. So let's take this value on the left hand side, AV minus lambda V equals 0. Then AV minus lambda V, I've multiplied this value with an identity function. And just in case you're wondering what was identity function or matrix, it's just a matrix with having all the diagonal entries as 1 and the other entries equals 0. From a quick recap, identity matrix multiplication is very similar to multiplying a scalar value with the number as 1. It's pretty much the same. But from a mathematical standpoint of view, it's more of a reflection. Say for instance, you stand in front of a mirror and then you ask yourself a question. The person do you see? Do you like the person? I mean, the kind of, the person inside, do you like it? If the answer is yes, that means what you're doing is right. But if the answer is no and you're not happy, that means it has to change, right? So the self-reflection aspect of asking yourself is pretty much what an identity matrix does. For a given expression, when you multiply that expression with an identity matrix, and when the value is reversed or reversal, or if doesn't equates to the previous value, then that means the function is not correct. But if it does, that means the function is correct. So identity function is nothing but just you're multiplying the expression with a 1. So I can actually write this as lambda IV, and then I can take the V out. This still has to be equal to 0. So A minus lambda I in the bracket V taken out equals 0. Just in case you still are not very comfortable that I actually changed this expression to this, let's take an example real quick and see that. So we have a matrix here. We know that AV equals lambda V, right? So A is this matrix, V will be a vector. We'll have a vector matrix which has 3 rows, x, y, and z. And then lambda equals x, y, and z as well. Now let's multiply. So when I multiply the first row, it becomes 7x plus y plus 3z equals lambda x. This becomes minus 3x plus 2y minus 3z equals lambda y minus 3x minus 2y minus z equals lambda z. This is the representation. I can actually club together all the x variables together, all the y variables together, and all the z variables together. So what do I get? This comes here, 7 minus lambda of x plus y plus 3z equates to 0. I have minus 3x, I've brought this here. The y is outside, 2 minus lambda, minus 3z equals 0. Minus 3x minus 2y plus of, we're taking these values out and this becomes 0. So this is the simplified representation of this value. Now let's just take out the variables outside again. This becomes 7 minus lambda. We've taken out all the x's out, all the y's out, and all the z out. So the left expression is 7 minus 7 minus lambda, minus 3 minus 3, 1, 2 minus lambda, minus 2, and 3 minus 3 minus 1 minus 1 minus lambda, x, y, z is out equals 0. Which is very similar to what you will get if you actually multiply lambda with an identity function and then you subtract it from A. Just quick reminder, this was identity function with 1s here and rest of all the entries are 0. So it's basically that a lambda is actually getting subtracted on the diagonal entries. So you see on these diagonal entries or the matrices, since we have 1, 1 here and we've multiplied lambda, so this becomes lambda, 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 and then we've just subtracted all the diagonal entries with the lambda. So this is pretty much similar to A minus lambda of identity function. You multiplying the lambda with the identity function and then this is all taken outside within a bracket which is multiplied with V, which is equal to 0. So you see that the previous equation is actually equal to this, which we proved already. So now let's get to the definition of eigenspaces. Very important definition, and I want us to really focus at this point in time. Alright, so let A be an n cross n matrix and let lambda be an eigenvalue of A. The lambda eigenspace of A is the solution set of A minus lambda I n multiplied with v equals 0. So it will be all possible values of the vector which will satisfy this equation, a minus lambda in multiplied with v will be equal to 0. It will be the solution set. That was the mathematical way of saying what an eigenspace is. Let's take a more visual aspect of understanding what an eigenspace is. So think of it as a container, a holder, some kind of a bucket which has a 0 vector inside it, okay? And then it has groups of eigenvectors. Let's say this is A, B, C. This is X, Y, and Z. So it has a group of vectors which has similar eigenvalue. So all of these vectors inside this box will have same eigenvalue, which is lambda, which can be any scalar value in this case, but they have same lambda value, which is eigenvalue. So this container is called as an eigenspace. So what is an eigenspace? First image is it's a box, and inside that box what do you have? All the eigenvectors which have similar eigenvalues. First thing. Second thing, a 0 vector. So that is an eigenspace visually. Now there's a third way of actually understanding this. Now it can also be said that lambda eigenspace is a subspace because it is null space of a matrix. It is a subspace because every subspace is actually a container holding some values. This is also a container holding some kind of vectors together which have similar eigenvalues, right? So this is also a subspace because it is a null space of matrix, namely this matrix. Now what exactly is null space? I'll just discuss that shortly. But what I want us to remember is if you have a null space of matrix, that means the first entry, that is A minus lambda in, should not be equal to 0. Just keep this in mind. I'll explain you what exactly null space of matrix is, and then we'll just get back to the slide again. So before we jump into null space, I want us to understand two more terms: subspace of a matrix and column space of a matrix. I've already explained these two concepts, but since they're so important and we need to, we really need to remember them, I'm just doing a quick recap again here. So subspace of a matrix. So let's see here, we have a field F which extends from negative infinity to infinity, and this field is actually of real numbers. So let's take out subset of this field, some subset, which will be called as vector space. Keep in mind, for a vector space to be a vector space of a field R, there has to be certain conditions. It is closed under vector addition and closed under scalar multiplication. When those two conditions are satisfied, it becomes a vector space. And then when you take a subset even of the vector space, it becomes a subspace. But for this vector space to be a subspace, it needs to satisfy three conditions. What are they? The first one is the 0 vector of V is in S. So if there's a 0 vector here, there has to be a 0 vector here as well. This is condition number 1. For each U and V which are in S, U plus V is in S. So for instance, if my V is 2, V vector space is 2, 3, 4 and 5. So my subspace S should be like 2, 3, 5, 4, 8 and 7 maybe. Why? So because 2 plus 3, 5 is also here. Then 5 plus 3, 8 is also a part here. So basically it means that when you add the entries, the value that you get after adding is also part of your set. So this is the second condition for a vector space to be a subspace. The third condition is you have some form of a scalar 1, 2, 3, 4, 5, and then you multiply it with your value. You should get the value back, and it should be in the field set. You might or might not get the value back, because if you're multiplying the value with 1, it's only then you'll get the value back. But when you multiply it with the scalar, the answer that you get should also be a part of your set. So for instance, if this 2 was multiplied by 2, I should be having a 4 in my subspace field, because I have multiplied this vector with a scalar, and then the value that I obtained after multiplying the 2 should also be a part of my subspace. So these are the three conditions one has to satisfy for a vector space to be a subspace of matrix. Quick recap, what are they? Zero vector is a part of the subspace, first important condition. Second important condition, when you are adding the two vectors, the value that you obtain after adding the two vectors should also be in your subspace. And then the third condition is you take any scalar, multiply that with your vector, and then the value that you obtain after multiplying the scalar with the vector should also be in your subspace. So in your field set or whatever subset you've extracted. So if these three conditions are satisfied, it's only then a subspace is created from a vector space. Next important term is column space of a matrix. So the column space of a matrix A is the vector space made up of all linear combinations of the columns of A. This is typical mathematical definition. Let's just skip it. Okay. Very simple visual understanding is you have a matrix here. Let's look at the columns. The entries in my first column are 1, 2, 3, 4. The entries in my second column are 1, 1, 1. And the entries in my third column are 2, 3, 4, 5. This one is unique. I don't see any other columns having similar entries. This also seems pretty much unique because I don't see any other columns having these entries. Let's have a look at the third column, 2, 3, 4, 5. This also looks unique because you don't see any of the columns having these entries. But hey, wait, what? When you add the first column and the second column, you are actually getting the value of the third column. 1 plus 1, 2, 2 plus 1, 3, 3 plus 1, 4, 4 plus 1, 5. So this column is actually dependent on the addition of these two columns, right? So this is not contributing anything to this matrix in itself because it's just a redundant value obtained by adding the first two columns. So we can skip this column. And so the column space of this matrix is actually a two-dimensional subspace of R4. Why R4? Because we have 4 columns. So the dimensionality of space is actually the number of rows in case of a matrix. So how do you remember column space of a matrix? You have to ask yourself this question. Does each column contribute something new to the subspace? Is every single column contributing something to the subspace? If the answer is yes, so for instance in case of first row, is it contributing independently? Yes. Second row, first column, it's column. First column contributing something independently? Yes. Second column contributing something independently? Yes. Third column? Nope. It's the addition of these two. So this is not contributing and hence it's not a column space. That's how you have to remember. Every individual column should be totally independent of each other. Now let's get back to the null space of matrix. Whoops. The most important definition, yes. Null space of a matrix. Remember our original discussion? That's what we were discussing. In the eigenspace, what is a null space of matrix? So the null space of a matrix A is the collection of all the solutions to the equation AV equals 0. So you're trying to find all the values of the vectors such that when you multiply the matrix with those vectors, you actually get a 0 back. So that is the null space of a matrix. It has to satisfy this condition. A dot V should be equal to 0. But keep in mind, we've already seen that V, which is eigenvector, can never be 0. We've already seen that, right? Eigenvalue might be, but eigenvector cannot be 0. Neither can this be 0, and A is a function here, a transformation. It's like you are taking a vector and then putting it inside some function. So even A cannot be 0 in case of null space of a matrix. This brings us back to our discussion. If you recall, A minus lambda of identity function should not be equal to 0. I asked us to remember this point. Remember in just a few slides prior to this discussion. Why is it? Because we want A multiplied by V equal to 0. Neither can this be 0 nor can this be 0. So that is why this should not be a 0 entry was the condition. Let us take an example here. Here we have A as 1, 2, 3, 1, 1, 1, 2, 3, 4 and V1, V2, V3 because we don't know what these values are and this is 0, 0, 0. So now we have to find the value of V1, V2, V3 such that when we multiply these two together we get 0, 0 and 0. And it's not too much to think right now at this point, but the values which will satisfy this condition is 1, 1 and minus 1. So if it's 1 here and minus 1 here, it's like 1 plus 1, 2, and then you're subtracting it from this value, so this becomes 0. Again, 1 is 2 here, this is 1, 2 plus 1, and then you're subtracting it. Similarly for the third column. So we're actually getting all 0 entries here. So then the null space NA consists of all multiples of this vector. So if you were taking 1 multiplied with 2, so this was 2, 2 and minus 2. So even 2, 2 and minus 2 would actually satisfy this condition. 3, 3 and minus 3 will also satisfy the condition. So any scalar multiplier that you multiply it with this vector will actually satisfy this condition. And so this is the null space of this matrix. This is the null space. So what is null space? The values of the vectors for which when you multiply the vector with those values, you get 0, 0, 0 on the right hand side. So this null space is aligned in R3. Alright, so yeah. Now let's get back to our previous definition from our previous slide, what we were discussing. This means that A minus lambda IN should not be equal to 0, because we've discussed that AV is equal to 0. So we're trying to find the value of V's for which when you pass those values inside this transformation or this function, it should be equal to 0. So neither of them can be 0 values. We've already seen eigenvectors are never 0, and even this cannot be 0. That is why we said that A minus lambda of IN should not be equal to 0, because it is a null space of matrix. Now does it make sense? I hope it does, but if you have questions, just drop them in the comments. I know it's a little tricky to get hang of. So example for basis of eigenspace. Now let us take an example. We have eigenvalue as lambda equals 3. Find if lambda is the eigenvector for matrix. That is what we are supposed to find, first question. And if so, compute the basis for the lambda eigenspaces. And if it is true, then we have to find the basis for the lambda eigenspace. So let's take the first condition will be for 3. So if 3 has to be eigenvalue for A, if and only if null matrix of A minus 3 of I2 should not be equal to 0. We've already seen this condition that this cannot be 0. AV equals 0 was the condition for null matrix. Neither can A nor can B be 0 in this case. And A, we've extended it as A minus lambda of identity function. We've already seen that as well. So this can also not be equal to 0. So let's put the values like this. We have 2, minus 1, minus 4, minus 1. This is my matrix minus 3. Then we have the identity function, which is 2 cross 2 matrix here, because my matrix is a 2 cross 2 matrix. This is 1, 1, this is 0 equals. Let's just do the computation. You're just multiplying this with 3 and 3, and then you're subtracting it. So 2 minus 3 is minus 1, minus 4 because we have 0 here. This is 0, so this will be minus 1, this is minus 3, and this is minus 1, so this becomes minus 4. Now let's just take out the negative sign outside and put it across the right hand side. So it'll just be all positive values, 1, 4, 1 and 4. Then let's bring this matrix in row reduced echelon form, which is RREF. In case you're wondering what is row reduced echelon form, I've already done a video on this, so just refer to that video, and this is pretty straightforward. Row reduced echelon form, that is, you're just subtracting this value from this and then this from this and getting a 0 and 0 here. So this becomes x equals minus 4y. Why the minus? Because we are taking this value on the right hand side of the equation. This is nothing 0, 0, so this will be y entries because this is x and this is y. We represent them in the form of parametric values. I have also discussed what parametric equations are. Just in case you've not checked that video out, you can do so. I'll link the URL in the description box. So we take out x and y from this. We're taking out the common y value. This becomes minus 4 and minus 1. So what does this mean? This means that we have one free variable available, y. So since y is a free variable, the null space of A minus 3 of I2 is non-zero. So this is not 0 because we have a free variable left. So 3 is an eigenvector. So it is an eigenvector. And what are the bases of these eigenvectors? Minus 4 and 1. So a basis for lambda eigenspace, here lambda value is 3, so 3 eigenspaces minus 4 and 1. This is how you compute the basis for a lambda eigenvalue. And how do you determine if it is? When you have some free variable left. That is the condition. So that's pretty much it for this session. There were some important terminologies we've discussed. It might sound a little confusing what exactly they were, but just to do a quick recap, we've understood what an eigenspace is. So what an eigenspace is, just think of it as a container. It is a container holding a 0 vector and then more vectors who have similar eigenvalues, which is lambda in this case. So that's my eigenspace. We've also seen what exactly a column span is, and we've also seen what exactly a null matrix is. For a matrix to be a null matrix condition, A dot V, that is the matrix multiplied with the vector space, should be equal to 0, which also means neither of these two entries can be 0. Neither can the transformation function be, nor can the eigenvector be. We've already seen we never get an eigenvector which is equal to 0. So that's actually pretty much it that we discussed in this session. If you still have any questions, feel free to get in touch with me through the website. So thank you so much.